Hello everyone, my name is Kesse. I'm Control and Automation Engineering student at the Federal University of Santa Maria, and now I'll be presenting a work titled Comparison of Visual SLAM Algorithms, more specifically ORB-SLAM2, RTAB-Map and SPTAM, in an indoor and outdoor environment with ROS. And in the introduction, I'll be showing the objective of my work and what is the problem that involve the Visual SLAM. And in the theoretical background, I'll be showing the modules diagram system of the RTAB-Map and ORB-SLAM2, and what is the type of cameras that normally used in these algorithms, and the difference among these cameras. It's very important. And the materials, it's basically the software that I use in order to do the simulations on the ROS. And for example, the robot that I use or the language, the programming language, and so on. The methodology would be basically the methods that allowed me to realize these simulations, like the how I get the ground truth for comparing to the accuracy of the Visual SLAM algorithms that I'm showing here, and the results would be obviously the results that I obtained with the simulations, more specifically the results related the accuracy of the robot trajectory, graph, and so on. And finally, the conclusions were basically my final conclusions of these experiments. There were 4 conclusions, by the way, and I'll start now with a brief introduction and overall what these algorithms are. It's basically to build a map and self-localization at the same time using cameras, obviously, and it can be monocular, stereo, and RGBD cameras, and so on. And the objective here is to compare 3 visual simultaneous localization and mapping algorithms applied to mobile robotics at the ROS. Like I said, ORB-SLAM2, RTAB-Map, and SPTAM. And that's the modules diagram system of the RTAB-Map, and there are 3 types of cameras that's more used in these algorithms, and it's basically monocular camera, RGBD camera, and stereo camera. And monocular camera is one simple camera that gives us images, and the RGBD cameras, it's basically the same but with a depth sensor. And finally, stereo camera basically are two monocular cameras separately each other for a certain distance. And how you can see, send the images for visual odometry module, that's basically estimate the pose with images, and after that send the frame and pose for other module, then add the keyframe to graph, detect loop closure and graph optimization to do the odometry correction and build the map 2D or 3D. In my case was 3D, obviously. And that's the modules diagram system of the ORB-SLAM2. The ORB-SLAM2 work with 3 threads working in parallel. There are tracking, local mapping, and loop closing. On the tracking, it's done the image pre-process plus a track local to generate the keyframe. And for the local mapping, it's done the keyframe insertion plus local body adjustment. And in the loop closing is done the loop detection plus loop correction, and finally it's done a map update and full body adjustment, and the final of the whole process. And these are the software that I use and the ROS to make the communication of the robot. It's very important. The gazebo to create the simulations of the environment, and the Hervis to visualize the results of the mapping and tracking, the Collab platform to process the data that would be the pose estimate of the Visual SLAM, and finally the Python and C++ to programming languages. And that's the robot that I built in order to make these simulations. And that robot is named the Robot Differential Drive. He has two cameras, more specifically RGBD and the stereo camera. And that's the environments of the simulations. These environments can be found in the gazebo, and an indoor environment is basically a museum, and the black arrow, it's where the robot will do your trajectory. But the question is how I get the ground truth trajectory to compare to the estimate trajectory of the Visual SLAM. And basically I used the undermath of the robot to get your odometry with you can predict the destiny spot. It's easy to do, and I'll show in this video 4 simulations. I'll get started now. And how you can see, the RTAB-Map created a 3D dense mapping, and on the other hand ORB-SLAM2 created a 3D sparse mapping. We have here RTAB-Map, RGBD, RTAB-Map stereo, and ORB-SLAM2 RGBD and ORB-SLAM2 stereo. And in the first simulations, more specifically RTAB-Map RGBD, and the end of the trajectory, the RTAB-Map got trouble because the RGBD camera is limited due to the short depth detection. Finish. And the results, and finally the results, you can see the left and right RTAB-Map RGBD indoor and RTAB-Map stereo indoor, and the trajectory estimate plus ground truth respectively. And one interesting thing, it's you can see in the final of the trajectory, the algorithm got a noise due to the lack of visual information. And over here we have the ORB-SLAM2 RGBD indoor and ORB-SLAM2 stereo indoor respectively. And over here we have RTAB-Map stereo outdoor and ORB-SLAM2 stereo outdoor respectively as well. And the RTAB-Map stereo outdoor got the great estimate trajectory, how you can see here. And over here we can see the SPTAM stereo indoor and SPTAM stereo outdoor. And these are the measurements of the trajectory distance, and how you can see the better performance was the ORB-SLAM2 RGBD indoor. He got more or less 6% of zero, and the RTAB-Map stereo outdoor he got for about 4% of zero. And I got 4 conclusions about my simulations. And my first one, unfortunately the RGBD camera, more specifically Kinect, cannot provide a trajectory because of the lack of feature and limitation to capture depth for long distance for outdoor environments. And the second one, the RTAB-Map stereo, showed a more accurate estimated measurement for outdoor environment. The third one was the ORB-SLAM2 RGBD showed to be more accurate for indoor environments. And finally the ORB-SLAM2 had the best accuracy in the measure of the trajectory distance. Thank you.